Welcome to the Cosmic Pie Podcast, Season 2, Episode number 16. I'm your host, Wayne Barkhouse, and here with me is...
Robert Moore.
We are broadcasting live from Grand Forks, University of North Dakota. If you have any comments or questions that you'd like to ask throughout the podcast, please feel free to use the live chat feature. Now, before we introduce our very special guest, just as a disclaimer, any of the opinions that Robert and I present, of course, are our personal opinions and not necessarily the opinions of the university or any other organization or unorganized people.
Or unorganized. That seems to be more the case.
Yeah. So, Robert, you want to do the honors today?
I will do the honors. With us today is Dr. Misty Bentz from Georgia State University. I'm doing the honors because I will go ahead and mention that she was on my master's committee for giving me that degree. But it's been a little while.
Does that mean I can ask her if she regrets it or not?
I don't know. I tell you, it made enough of an impression on me, especially since I will say you gave me some of the best comments on that thesis. I still have the copy that you gave back to me. So... Oh, yeah. I still have that. I pull it out for some of our graduate students here and say, okay, this is the type of comments you can expect. Hopefully, anyway. But she is a professor, again, at Georgia State University, working with, I think, if everything is working in my head, AGN, so active galactic nuclei, which entails some work with black holes, which you mentioned that NASA has declared this Black Hole Day. So...
Week.
Oh, week.
Yeah.
A whole week of them.
See, there's so much to learn. You can't just learn all in one day. You need a whole week to talk about it.
Sitting in on your general relativity class this semester, I will say, that's definitely the case. There's a lot to learn.
Yeah, for sure.
So,
So Misty, do you want to kind of maybe, instead of jumping into research topics, maybe give a little background of why you became interested in science to begin with and those sort of things?
ah. Oh, Lordy. Weren't fast enough getting that pause button, huh? That's a good way of putting it. I like that.
It's also a little cleaner.
It is cleaner.
So one of the things that Robert mentioned at the beginning, we talked about black holes and AGN. Do you want to describe, for a layman's perspective, what is a AGN and how they relate to black holes?
Uh-oh.
That there's a whole bunch of light coming from a very small point right in the middle. And that is the signature of rapidly accreting black hole.
I hate to interrupt, but we're apparently not hearing you. How about now, Millie? Can you hear Misty?
Hello, hello, hello.
Having technical difficulties.
Uh-oh.
And that's not surprising me for some reason. Okay, now he hears you. Okay.
Okay.
So let's go back over the explanation of the AGNs. I hate doing that, but that's
Sure.
kind of important.
Yeah. Let's make sure that we get that out to everybody. So an AGN, it's an active galactic nucleus. Is the acronym. It is really just an accreting black hole, so a black hole that's eating a big meal right now. And so we see a lot of light emitted from the center of a galaxy, and that light is coming from compressed and superheated gas that is falling into the black hole. And when you superheat a gas, it glows really, really brightly and gives off a whole bunch of light. And so we see these beacons of light in the centers of galaxies that tell us when a black hole is having a big meal. Most galaxies today in the universe are not actively eating very much. They might have a little snack now and then. The black hole in the center of our galaxy is really not doing anything. It might nibble a little here and there, but it would not be considered an active galactic nucleus if we were to see it from outside of our galaxy. It's quiet. And so these are fairly rare in the local universe, but they were much more common in the early universe when there was just much more gas available, but also when things were a lot closer together and a lot smaller. And so we've seen an evolution over the history of the universe in terms of how black holes are growing as a function of time.
Now, Misty, kind of one of the amazing things that I guess related to black holes was back a few years ago where the Event Horizon Telescope imaged the black holes, M87 in the Milky Way eventually for the first time. In some sense, even prior to that, I remember there was a holdout, at least for a small minority of scientists. So I'm not talking about people who have their own ideas that go on, YouTube or some other social media and spout certain things. But, professional scientists actually not quite sure if black holes really exist. And when I think about it, my eye was because if you do accept that black holes exist based on, evidence before the Event Horizon Telescope, like the motion of stars, for example, around our Milky Way black holes, then you go down this rabbit hole of trying to figure out, well, if they exist, then what actually happens in their very center, the singularity. So, first of all, what's your opinion on, the beauty or the if you like, the advancement in black hole science with the Event Horizon Telescope, and what does that now force us to do when we want to have a better understanding of the true nature of black holes themselves?
Yeah, so I'll say the type of research I do is fairly different from what the Event Horizon Telescope team was attempting to do, even though it's all related to black holes. And so the two black holes that they studied have a little bit of gas around them that they're snacking off of. And so M87 in particular drives a pretty fun optical jet. So there's a jet of material that gets spat out from close to the black hole, and we can actually see that in visible light quite clearly in images of the galaxy. So that's another sign that the black hole is there and doing something. The Event Horizon Telescope images, when they first came out, I was really hoping it was going to be the Milky Way black hole first because I was more curious to see what they would find with that one. But M87 was pretty fun too. It was a lot of fun to be a black hole astronomer at that time because basically the entire world was talking about black holes for a day or two when that image came out. I had a few people who interviewed me ahead of time saying, so what are we going to see when they have this big press release? And I remember noticing that a lot of the simulations that were being shown in news articles like, oh, this is similar to what we might see in the press release that's going to come out. A lot of those simulations were really high resolution with a lot of detail in the structure of what the gas might look like around the black hole. And apparently I captured something before it happened because I figured that people were going to be a little disappointed when the images weren't quite that sharp and crisp and
Right.
clear. And then there were all of the comments about like, why is it fuzzy and why didn't they take the lens cap off and all of those things when the images first came out. So one of the interesting ways that results aligns with my research is they were able to use the data from the Event Horizon Telescope to constrain the mass of the black hole. So if a black hole is a thing, it has mass because there's material falling into it, and that mass is highly compressed. And so we detect the black hole through its gravitational influence on things around it that are visible, that we can see with telescopes. And so knowing how much mass is in a black hole is an interesting question for many reasons that we can get into. But they were able to constrain the mass of the black hole and compare it to some estimates or measurements from other techniques that had been done for that same black hole. And so that's an active area of research where I'm very busy, is trying to measure the masses of black holes through their gravitational influence. So that was probably the thing I found personally most interesting about the results. When it came out time for the Milky Way Sagittarius A star results to come out, so Sagittarius A star is the name we give for the black hole in the center of our galaxy. It was interesting to see what constraints they also had on the spin of the black hole, how fast it's going around.
Oh, right, yeah.
As well as what they think the inclination angle is. So if it's spinning around, it has some preferred axis of rotation. And so what is the direction of that relative to our point of view? And I believe the constraints had the rotation axis pointed directly at us, which is not what I would have expected, actually.
I missed that part. That's weird.
It is weird. And I think it was a somewhat weak constraint, but it's still one of those things that I find perplexing because there is some evidence that our black hole was active in the recent past. There are these what's called Fermi bubbles. So these are gamma ray bubbles that come out of the Milky Way center, and they're aligned sort of perpendicular to the spiral disk of our galaxy. And so you see these fountains going up above and below the plane of the galaxy. And that would seem to indicate that if they're related to the black hole, which is sort of how I interpret those features, that the black hole should not be aligned with our line of sight. It should be more perpendicular to our line of sight. So I think there are a lot of mysteries still about those results. And, there's some limitations to how much they can constrain with the data that they achieved. And they continue to improve on the amount of data and the quality of the data over time as well. And so I think we'll get some more answers. But in terms of what does this mean for the inside of the black hole, that's I like to tell my students that's I feel like more of a philosophy question than a science question, because we can't get any information out of the center of the black hole. And so we can't make any measurements. And so we can make a lot of guesses, but we can't actually test them really.
Right.
And I like to have that same cop-out answer when the idea of multiverses and things come along too. Like, that's an interesting idea. We could play around with the what ifs about that, but I honestly can't go out and measure anything about it. So I can't give you any real answers. So I think I'll leave it there and see how you want to follow up on that.
I mean, that's fair, because we speculated in one of the classes I took on the cold molecular clouds potentially being a living thing.
Oh, geez.
Because, we started pointing out they have an energy source, the stars embedded in them. They have magnetic fields that connect the various portions of it and can signal through it. And, we were like, wait a minute.
When you get down to it, there's a lot of really fun philosophical questions associated with astronomy. Some things are just too big and too difficult for us to actually test. So,
right.
And a lot of this gets sort of on the edges, like when you start talking about wormholes being portals to black holes in other universes and things like that. Like, that makes for some great science fiction, but until we figure out how to measure these things, they tend not to appear so much in our science.
Right.
So when we talk about AGN, so the two major ingredients, of course, is the supermassive black hole with the accretion disk. Now, the point about the supermassive black holes is, as far as I know, I'm not an expert on this field by far, is that they're found in most ordinary larger galaxies. When we talk about like low mass galaxies, dwarf or satellite galaxies, then that fraction of those galaxies that contain these supermassive black holes is a lot smaller than for the larger mass black holes. So one of the interesting thing, of course, is what came first. The chicken and egg question.
Mhm.
Did some mechanism or mechanisms form that supermassive black hole, and then the rest of the galaxy kind of formed around that, or do you need some kind of hosting medium, a proto galaxy that ultimately, in most cases, would lead to the formation of a supermassive black hole in the center, at least for the larger mass black holes? So, what's your feeling on that in the research that you have done?
Yeah, so I'd say I agree with almost everything you said, but I would clarify one thing, which is that in the satellite and dwarf galaxies, we actually don't have a good measurement of how many of those have black holes in them, because the black holes are small enough that they're very difficult to detect. So they're really at the limits of what we can do with our observational tools, which is why we can't say as easily whether or not they're there. In some cases, it's pretty clear that they are, but it's much harder to say that they're not if we don't see something obvious. So that's actually an open question. It's called the occupation fraction. So what is the occupation fraction of low mass or dwarf galaxies? And that's actually a place where a lot of scientists think that with some new tools that are coming online in the near future, we might be able to start trying to answer this chicken or egg question, because some low mass galaxies can be thought of as analogs to the first galaxies that started growing and forming in the early universe. And the question of which came first relates to, what are you starting with in terms of your supermassive black hole? Are you starting with a big heavy seed, or are you starting with lots of little lighter seeds? So what starting point do you have that you then grow into a supermassive black hole? And we don't actually know if you start with heavy seeds or with light seeds or maybe something in between, but that plays into the type of formation mechanism that you might have, as well as the occupation fraction for what you would expect in low mass galaxies, some of which we can try to explore in the nearby universe. So there are still a lot of open questions in this particular research area. James Webb Space Telescope, which I hope your listeners are familiar with, that was one of the key science areas for JWST. Is by having an infrared optimized telescope, you can try to look much further back in the universe. So looking back to the much, much earlier galaxies to try to start to find the very first galaxies and see, do they have monster black holes that are already gobbling at high rates in the very early universe, in which case maybe the black hole comes first and the galaxy sort of grows around it, and that might indicate a heavy seed kind of formation mechanism? Or are we seeing galaxies that don't appear to have black holes in them in the very early stages of the universe, and so maybe you need the galaxy first to sort of grow the little light seeds that will sink to the center and start building up your black hole? There was actually just a paper today, that used a sample of 6 galaxies, which isn't a very large sample, and they didn't actually have measurements for all 6 galaxies. They had some upper limits for 3 of them, I think. So with just a handful of objects, they were saying that they had a little tentative evidence that maybe galaxies and black holes, maybe it's an inside-out growth. So maybe a heavy seed and a big black hole, and then the galaxy sort of grows up around it. But, it's really hard to draw any firm conclusions with 3 measurements and a handful of upper limits. So these are big areas of research right now. Lots of teams are spending a lot of time and energy trying to figure out how we can try to answer these questions. And it has a lot of implications for how galaxies have evolved as a function of time and why they look the way that they do today.
Yeah, you kind of wonder how the seeds build up, because you're not talking about things that are tens of solar masses, but for low mass galaxies, hundreds of solar masses for sure. So
Yeah.
it's hard to envision how even a star cluster that contains a weird situation where it only formed really high mass stars. So in astronomy, the initial mass function would be skewed from what it would be in our own galaxy to produce rapidly these very high mass stars that have essentially no metal, so it allows them to go through their life really quickly for being such high mass. And of course, they can be really high mass stuff, if my understanding, if they do have a low metallicity. So well beyond, like the standard or fiducial, like 100 solar mass limit. Maybe these are 200 solar mass stars or whatever. But you need a lot of them to come together quickly, right? So they need to be near each other, so gravitationally bound in a close cluster. That's the only way I can think of that you would form such a supermassive black hole in such a short period of time.
Right.
Yeah, so there are other ideas too. There can just be a direct collapse into a massive black hole. And so you can have very strong density fluctuations in the early universe that just create black hole seeds directly. So, don't pass go, don't collect $200, just collapse directly into a black hole. There's no star that was formed. It just went straight into a black hole. And so that's another idea for a way to have heavy seeds around very early in the universe. But no matter what seed you have, we still have another problem, which is just that we don't understand how they get so big so fast, because they would have to be eating at a very high rate for a significant period of time to get to the monster sizes that we see in the early universe when we are looking at the typical quasars that people talk about. So this is like 10 billion times the mass of the sun. So if you can think of 10 billion suns all collapsed down into a black hole, that's a lot of mass. And we're seeing that when the universe is 1 billion years old. So there's not a lot of time to build up something that massive. Whether you start from light seeds or you start from heavier direct collapse seeds, that's still a problem. So we're still working on that one too.
Yeah, first thing I think of course, is any spin, rotation, angular momentum would be an issue, right? If you have a very large cloud of material that's going to collapse. But if it's rotating, doesn't that hinder that type of collapse, and certainly would affect the time scale in which such a thing could form a black hole?
Right. And when you're dumping a bunch of material onto a black hole, that material ends up shining very brightly, and that creates a pressure that starts blowing the material away too. So you have this sort of self-regulation. It's like, how can you dump that much material on without it just blowing it all away? That's another question of how can you sort of super feed your black hole to grow it over a very short period of time. So lots of questions here, no end of questions.
Well, I just thought of a solution. So it's used Gupta from the University of Ottawa, who claims the universe is 28 billion years old. That gives you enough time. And that's published now, 2 papers out of that work, quote unquote. So what do you I mean, Robert and I were debating this, on a previous podcast. One point of view, if I'm going to play devil's advocate, would be, okay, of course, if I was a reviewer, I would never let that pass. It doesn't hold up to the scrutiny of things that we know already. But then the other side of me says, well, let's get it out there so then we can go after it, right? The scientific way of double checking, triple checking, critical thinking, constructive criticism, and attack it that way. But of course, once you release it to the public, you get all of these non-scientists, non-experts who immediately accept it as gospel truth. And right away, the universe has been turned upside down. It's now 28 billion years instead of 14 billion years old, so on and so forth. So what's your personal feeling about that kind of stuff?
Yeah.
I was going to say I could tell what your reaction was while he was talking.
So that's obviously, that's bait for all of those headlines like scientists baffled, right? Like when in fact most scientists are not baffled. This is just one person with a particularly interesting set of ideas. As I understand it, the basis for his claim is that the speed of light is not constant as a function of time. That's how he gets to all of these grand conclusions. I think I would want to see some evidence to back up that claim, because I don't know of any that exists. And so I think if we're going to take it seriously, then there's a lot more groundwork that needs to be laid. So, what I tell my students in intro astronomy when, they're taking their last science class ever before they go off into the wide world, and you just hope that they retain something, right? I tell them that science, we do the best we can with what we have as scientists, right? We use all the evidence available to us at the moment in order to try to come up with a clear picture of why things are the way they are. Why are they behaving this way? Why do they look this way? Where did they come from? And that doesn't mean that's the best picture ever. It's just the best we can do with what we know. So of course things can change when you get new information. So that's why scientists baffled should never actually be a surprise. We should always be baffled because we should be asking new questions and looking with new tools and trying to ask,
Job
trying to
security.
find new things. Yeah. Our job is to be baffled. Our job is to ask questions and hopefully find some answers. But also that, you don't just throw away centuries of well-established and duplicated work on an idea that doesn't have a lot of evidence to back it up, right? So
Right.
grand claims require really strong evidence. So I think a lot of people do like to, release sort of provocative ideas, and some people do that because they like the attention that generates. I'm thinking of someone else in particular in our field. And that can be an interesting role to play because it's not a bad idea for all of us just to stop every so often and question things and think about them and remind ourselves, why do we think that? Oh, right, because of all of these lines of evidence. That's why we think this. And sometimes those questions do actually identify weaknesses in our logic or in our piles of evidence, but I think this one is on pretty shaky ground. I don't think it's supported well enough to take it very seriously. It's an interesting thought experiment, but it doesn't have the evidence to back it up as far as I understand.
Yeah, one of the things I think of when you hear like, some major announcement and a legitimate major announcement, and a classic example would be 1998 with dark energy, the accelerated expansion of the universe, is I like to look back on that and say, okay, how did we miss that in the past? And you find out that there are sometimes, obviously hindsight's 2020, but there are these little signposts that appear that you may or may not have taken seriously in the past, which indicated some issues. And I remember this would have been somewhere around probably 1994, 1995, where there were papers being written that the cold dark matter formalism, which is basically an explanation of dark matter and how the effects propagate through our universe, wasn't quite right because of the mismatching we were starting to find based in simulations and structural formation. If you think of statistically how you would measure the distribution of galaxies and structure, you can use different what we call the correlation functions. That these were not meeting expectations, if you like, when we based it on the best simulations we had in the mid-90s. And that was pointing, of course, to the missing ingredient being the dark energy aspect of things. Right. Some people had written about it. Now, of course, I'm not picking on theorists, but if you're a theorist, your job is to write papers based on the best knowledge you can. And those papers could be include different models in science. And maybe that's where non-experts, non-scientists go wrong. They think if someone publishes a paper on some model, there's got to be some lot of truth to that. Not necessarily, right? There could be, 100 different models trying to explain some aspect of the universe, for example. But if you get lucky and one of those 100 happen to be pointing in the right direction and you don't know it at the time, you really just got lucky. There's nothing that says that one model was better than all the other 99 that you had published. So if we go back a little bit prior to 1998, there were some indications from certain people that, yes, dark energy had to be there. There had to be this, accelerated expansion, to the universe because we needed that mass/energy density to make everything work out cosmology-wise. So it's interesting always to go back, I find personally, a little bit to see, okay, where were the clues? And they're really subtle. It's like a Sherlock Holmes mystery, right? If you're not on the ball and really thinking hard. And the other thing, Misty, maybe you can address this, is that sometimes when we learn things from our professors and, at higher education, that our mind somehow gets trained into that line of thinking, that it really takes a lot of work to go outside the envelope and to maybe think of things from a totally different point of view. It may help, it may not help, but we get so locked in of just like this template that we're forced to be in, this mold of thinking. Do you find that's the case?
Oh, all the time. Yeah, definitely. And I see this a lot with my graduate students, bless their hearts. They're like, oh my goodness, you must know everything, my professor. And so, you give them some background information on a topic and, there's bits and pieces there that, may relate to the project that they're working on, but you're not necessarily giving them the whole story, sort of encouraging them to go read the literature and make sure that they're seeing all of the different pieces that are out there. And, we are all humans. We all have our own specific ideas in our own research area that might disagree with other people's ideas. That's why it's research, right? We're
Right.
all asking questions, and sometimes we come up with different answers, and then we have to defend them to each other. But yeah, I can definitely see, my little biases get imprinted on my students, and I try to, sort of encourage them to think for themselves as they get their feet under them and they get more familiar with the techniques that we use and the literature in the field and things like that, so that they can develop their own biases and not just copy mine in the future. But that's a normal thing that we sort of have to work on as scientists. We all have our own biases. This has popped up over and over and over again in science history, and sometimes that just comes from being someone who's been in the field for a long time and has held an idea for a really long time, and then some young whippersnapper comes along and challenges our long held traditions of what we think we understand, right? And so there's those dynamics that play out. And you were talking about the discovery of, or the announcement of just dark energy, and one of the interesting things about that particular discovery and why we were sort of able to adopt that paradigm changing idea so easily is because there were two independent teams of people who were competing and not necessarily always very nicely with each other, and they came to the same conclusion, independent with their own data. And so, when you've got groups of people who are not necessarily inclined to agree with each other coming to the same conclusion based on, a huge investment of time and resources and research, then that's always going to help you adopt something that's different than what you thought. It's rarely the one random guy shouting in the corner about his idea for how Einstein got it all wrong that ends up being the person who changes the paradigm. You need
Right.
teams of people working on these, and when more than one team comes to the same conclusion, it's a little easier for everyone to sort of follow along with where we're going.
Now, Misty, you mean I receive these emails, several of them per year? I mean, these guys are. Right? You get these emails where Einstein is wrong and here's the reasons why. And it's like, please don't send me an email anymore. And they never listen.
Yeah, I found the only thing you can do, like if I tend not to open them, and if it's the same repeat offender, I tend to eventually just block them
Yeah.
because I get too many emails. But I do know some other people that like to try to have conversations with these people, and I admit I don't have the patience for it because I'm usually too busy with 20 other things to
Yeah.
deal with
I
that.
remember one time I received a book from somebody like this, and I opened up the envelope, and of course the first thing I did is look for white powder because this was at a time where that was going around type of thing.
Oh, Lord,
So
yeah.
you're pretty scared about it. I figured, well, I didn't want to get anyone else to open it, if it's addressed to me, and I
Right.
feel really bad if something bad happened to somebody else because of me, giving them my mail to open for me. So I opened it carefully, but people go out and self-publish a lot of this stuff now, right? So it's a lot
Right.
easier than in the past and then of course now you have online, right? So anybody can, like Robert and I can have a podcast, right? So you can go out and spout your ideas, and there's there's people out there that will listen to this stuff. But you mentioned the dark energy, and I remember when that was first announced, and my first thought, because science is conducted by humans, as you mentioned. So, and when I first heard about my bias was like, this is so messy, it's got to be wrong. Like if I was in charge, right, and to make a universe, that's not how I would make it, because it just mucks it up too much. And you mentioned about two independent teams, and that was something. But of course, right away, people said, okay, there's like gray dust sprinkled throughout the universe, right? And that dims the light from more so than what you'd expect. But to me, it was like after we had other techniques beyond just using these specialized supernovae type 1A, that there were other ways to measure the influence of dark energy. And that's, for me, is when I thought, okay, it might be messy, but that's the way things are. So you got to deal with it, and then move forward. But you mentioned
Yeah,
about, yeah, sorry, go ahead.
Oh, yeah. I was just going to say it's not a bad thing that you had that reaction at first, because that should be our reaction to, these bold claims is, hey, wait a second. Let's talk about this, right? And I don't know if you remember this, but several years back, there was a claim of, was it neutrinos traveling faster than the
Yes.
speed of light?
Yes.
Yeah, exactly.
Right? And that one, I think even the team themselves didn't really believe it, but they could not figure out why they kept getting this result. Like the result kept standing, and they ended up publishing it, or at least releasing press releases. I can't remember if they had published papers, but sometime later it got traced to just a bad cable connection in their experimental setup, right? And so that result did go away, but that should be our reaction to things that don't sound right based on what we know. And that's not a bad thing. We should ask questions, and we should, figure out whether we see any weaknesses or we see anything that's gone potentially wrong in the experimental setup and the conclusions that were drawn. We should be skeptical, but yeah, eventually, if the claim stands, enough other evidence comes along to help prop it up. And that's when, you can't just keep hanging on to your old ideas because you like them better. You do have to follow the evidence at some point.
Yeah, and just to follow up on that, so before we get to Millie's question,
Okay.
so, I'm thinking about the fact that Fred Hoyle, for example, well-known scientist at the time, absolutely, really, if you listen to what he actually, I don't know what he actually thought, right, his private thoughts on the matter, but he was a great proponent of the steady state model. So he was
Right.
against the Big Bang, and they always say, okay, that's where that word Big Bang, that term came from, right? And it was a negative comment he was making, I guess, to the BBC during some interview. And the idea that even in the mid-60s, when the cosmic microwave background was discovered, which ultimately leads to the awarding of several Nobel Prizes, not just one for the discovery, even he refused to accept that some other alternative beyond the steady state. He was so married to that solution, to that issue, to his way of thinking. It almost didn't matter what you would present him. He would always come up with some way to say, nah, that's not right because of blah, blah, blah. And then even though the odds of that not being right were so tiny, right, that it almost had to be right, you can never say absolutely for sure on anything.
Right.
Right? You just say, this is where the evidence is leading me. So, but yeah, people, like I said, like Fred Hoyle, even these eminent scientists and stuff, couldn't get rid of that idea that was ingrained in their mind, right?
Right.
Yeah.
And
Yeah, we had one of those in black holes too. So Jeffrey Burbidge, for as long as he was around, was a proponent of quasars not being at cosmological redshift, that they were being ejected from galaxies that were nearby. And that was another story of someone who had an idea that had some merit at some point in time, but that merit decreased over time until it was minuscule or maybe not existent anymore. And the weight of evidence on the other side was so high that really he should have accepted it and just couldn't bring himself to do it. And so, yeah, we get a few of those very high profile cases in our field every so often.
Now you remind me of someone, Halton Arp.
Oh,
right?
yes.
Right? So he's famous for looking at bridges of material that connect quasars to normal galaxies that are much closer to us. And he would say, okay, there's no way this bridge of material can connect a high redshift object to a low redshift object. Therefore, quasars are not at high redshift, right? It's the ejected material behind them away from us, giving rise to that high redshift measurement, if you like. And why I mention that is because Misty, Halton Arp, he's passed away several years ago. He actually contacted me a few years back, probably within a couple of years of his passing, just prior to that, of course. It would have been better if he contacted me after his passing.
That would have been
That would be a better story.
That would be an interesting story, yeah.
So what had happened was that for my master's degree, we published a study of a globular cluster population around two Higgs compact groups. And Arp had got a hold of that paper, and he was interested in one of those compact groups. There was, I guess, a quasar with the bridge of material attached to a normal galaxy in that field of view. And see, he actually asked me for my data for the imaging, and I sent it off to him. But of course, I never heard anything after that. But I was on two minds, right? Because I think I was a PhD student at the time. I'm thinking, should I send it to this guy and here's my images, but don't attach my name to anything that you publish, right? I still have to get a postdoc and a
Right.
faculty position.
And you
I
were
have
helping him.
I have a career and I have to worry about, right?
But we do have a question.
Yeah.
So from Millie Milford, if black holes are eating material now, black holes are eating material, how are they jets formed that shoot out material in AGNs?
Yeah, that's a good question, and one that we think we have some ideas about, but we're not fully sure. And so the jets end up coming from the material before it goes in the black hole, so it's not coming out of the black hole itself. Once something goes in, it stays in. And so this is material that's coming from the disk of material that's swirling very close to the black hole. And this is flattened in height, so it looks like sort of, do you remember those pogo balls? You could stand on the little platform and bounce on the ball. So it's a ball with a plate around the edges. That's sort of what we're thinking about in terms of what to have in your mind's eye. And so the material in the disc in that flat part is swirling around, and the inner edges of that disc, that's the material that's falling in the black hole. Well, you've got really highly heated ionized gas and very likely strong magnetic fields in that material before it falls in the black hole. You can actually wind up magnetic fields and drive things like jets of material out of these disks. So when we see really strong jets coming out of an active galactic nucleus, that's probably telling us something about the magnetic fields in the regions very close to the black hole. Very highly organized magnetic fields, very strong magnetic fields that sort of create these fountains that shoot out of the top and the bottom of that structure. But not all active galactic nuclei have strong jets. And so the question is, why do you get it in some of them and not others? And that's not something that we can fully answer yet at this point. We don't fully understand all the details of exactly what has to happen in order to create these jets, but we do see them and study them and try to understand them as best we can. So we think it's related to magnetic fields, sort of a hand-wavy magnetic field answer here. But it's certainly an active area of research. And yeah, we don't see them in every black hole, but we do see very strong and interesting jets from some black holes.
So, Misty, is that tied into, I forget how to pronounce the second name, the Blanford-Zajac or something like that mechanism?
Oh,
Or is that something
probably.
totally different?
I don't remember, honestly,
Okay.
because I don't work on the jets. The really strong jets tend to come from black holes that are not accreting at a very high rate. So, for example, M87. And so they're not the types of accreting black holes that I tend to study. I tend to study ones that are eating, a few suns worth of material per year, basically. So that's a fairly high amount of material flowing into them, because then that actually makes a lot of light shine out of the center of the galaxy. And so we can see them very, very far away, but also we have a really strong signal to try to understand what's happening with the material that's feeding the black hole.
So when you look at, like, you study the jets or even accreting material, a lot of it, of course, must depend on the alignment of the system itself, right? In terms of what observational clues you can use.
Yeah, and it depends a lot also on what wavelength of light you look at this structure with. So if you're looking at it with visible light, you see certain features. If you look at it with a radio telescope, for example, you see completely different things. And so we have all of these names, historical names that we've attached to actively accreting supermassive black holes that just came up over time because we were seeing certain objects had sort of similar properties when viewed in a certain way or a certain wavelength of light. And it took a while to understand that we were seeing the same structure, but just different, we were sensitive to sort of different properties of it. And also, if you look at it from different angles, and so if you look at it face on or you look at it edge on, that also, so the orientation that you view it at, you also see different things that way too. And so there's this whole zoo of names that we've given active galactic nuclei. And it's only within the last 40 years that we've really started to understand how all of these different properties are related to each other and in which circumstances do you get this but not that. And a lot of those differences that we see depend on the wavelength that you view them at, the orientation angle that you view the system at, And then how strongly is the black hole, how much is the black hole being fed right now? Is it eating a lot, or is it just eating a little bit? Because that can affect what you see as well. And so with, a lot of different, there's a few different variables to play with here, and a lot of different observational evidence to try to piece together. And so we call this the unification theory of black hole accretion disks. So yeah, that's something we're still working on to trying to figure out. And people keep trying to break that model, and they haven't quite done it yet. But we know we don't have everything settled quite yet at this point.
Now, Misty, do you find a higher fraction of AGNs when if let's say we're just looking at spiral galaxies, so maybe they're Seyfarts or whatever, that if you look at, let's say, compare barred spirals versus unbarred spirals, where barred spirals gives you sort of a conduit, right, of inflowing material, does that help propagate, or promote, I should say, the formation of an AGN and help supply material to the accretion disk, or is there really no connection between those two?
It's very unclear. People have for a very long time tried to determine whether bars are like a main fueling mechanism for black holes, or whether maybe it's mergers or close passes of other galaxies. And the time scales are so different for these kinds of features. So when a black hole is actively accreting, that process lasts for maybe about 10 million years. It's sort of our best average guess for how long that process happens. But a lot of these other processes, such as flyby of two galaxies, that's a much longer period of time. And then if that disrupts the gas in the edges of the galaxy to start funneling it towards the center, you could see how there might be a very long delay between the thing that triggers the feeding of the black hole before you actually start seeing the black hole being fed, right? And so at that point, the galaxies are very far away from each other. The bars themselves, there have been no conclusive studies to show that a bar helps or hinders with black hole feeding. It's really unclear. And so we still don't fully understand, what exactly is causing gas to be funneled into the center to feed a black hole. But it could just be that there are many ways for this to happen. And we have to take all of the time scale arguments into account when we try to figure out the causes. And sometimes that can be really hard to untangle.
I guess you're thinking about like some way, like losing angular momentum, right? To allow it to fall towards the center, right?
That's right. And, it could be that magnetic fields play a role in this. I know there are some people working on that right now with galactic scale magnetic fields, and whether that can sort of help drag material into the center as well. And so, there's many different avenues as to how you can shove gas into the middle of a galaxy and feed the black hole. But also, it doesn't necessarily mean that the gas goes in the black hole, even if it gets towards the center of the galaxy, because we see a lot of galaxies that have central stellar rings. And so if the gas gets stopped at some distance from the black hole, it can actually just compress itself and form a whole bunch of stars, and then there's no gas left to dump on the black hole. So yeah, it's unclear why some galaxies are currently eating and others are not. And it's probably unclear because there are many ways you can feed a black hole, but also not all of those are always going to result in the black hole eating. And so it's complicated. And I'm sure that's part of the reason why we haven't figured it out yet.
And in fact, it sounds like there's a lot of ways to stop it feeding than there are really to get it going in the first place. I mean, there's the radiation pressure.
Yeah, there's an equal number of ways of stopping the feeding as there are starting it.
Well, if you think about it, just from outside or something, you think, well, wait a minute, what do I need? Supermassive black hole. Well, as we talked already, if not all, almost all galaxies have that. So that piece of the puzzle is there. All we need is the accretion disk. Well, what has gas, right? Well, spiral galaxies. So why not locally? Does every single spiral not be an active galaxy then, right?
Right. And, they probably all have been at some point in their past. It's just they're not all right now. And so at some point, you will funnel gas into the center of a galaxy. I think best estimates are that every galaxy has gone through at least one AGN phase in its lifetime. I'm sure there's some mass limit on that, some lower mass limit. But if we're talking about, Milky Way kinds of average spiral galaxies, they've all been active at least once to our best estimates. But, because you can, if you start eating the gas, you use it up. You also start blowing some of it away when you start eating it. And it's only going to last for a certain amount of time if it's not replenished. And so even though they're not active right now, they may have been in the past. It's just they ate their meal and all the crumbs are gone and they have nothing left to snack on at this point. But yeah, spiral galaxies today, we do find that spiral galaxies tend to be more active than elliptical galaxies at this moment in the universe's history. However, that doesn't mean that all of them are, and it's only a small fraction that actually are. However, they probably all were at some point, even if they are not right now. May become again in the future.
Yeah, I was talking about a multivariable or a parameter type of model, right?
I got to throw in and ask because I don't know, but how about irregulars? Are they more prone to having AGNs than spirals?
Yeah, so it's really hard to figure out if you have an accreting massive black hole in an irregular galaxy because the way it works out, the less massive your black hole is, the less luminous it's going to be when it's eating. So the brightness of the stuff that it's eating is going to be less for a smaller black hole. And irregular galaxies are smaller galaxies. We know that black hole size or mass scales with galaxy mass. And so if you have a low mass galaxy with a low mass black hole,
it's not going to shine.
Eating, it's not going to shine very brightly. And so if it's not really nearby, it's going to be hard to see. And so that's one of the problems is we can't see those very far away. It also can easily be mistaken for a lot of other kinds of things that shine at similar brightnesses. So this is the problem with the low mass galaxies is that the signatures that we would look for based on a massive black hole, I won't call it supermassive at this point because it's probably, more like 100,000 times the mass of the sun instead of several million. There are a lot of different ways you can get those signatures when you're talking about them being smaller as they would be in that kind of a situation. So you can easily mistake all sorts of other things for a massive black hole in a dwarf galaxy. And there are a few ways that you can try to find them that are a bit more telltale signs of the black hole accreting. One of those is variability. And so we should see the brightness change. It flickers as a function of time. And so with repeated imaging over and over and over again, you can try and look for variable sources in small galaxies. That's something that the Rubin Rubin telescope is the Rubin? Yeah, Rubin telescope, the Legacy Survey of Space and Time, LSST, and then they've named it for Vera Rubin. That telescope is going to scan the sky over and over and over and over again, and it's going to build up movies of sections of the sky. And so that's one good way to try to look for potential massive black holes that are accreting in low mass galaxies. And so I'm excited to see what comes out of that. That telescope is supposed to come online in the next year. Is that right?
Yeah, late 25, I think.
Yeah, I think first flight is in about a year or so. They've certainly been making a lot of progress with the construction anyways, but that'll be one interesting way to try to find these potential black hole seeds in nearby low mass galaxies that are analogs of maybe what galaxies look like in the very early universe.
So these like intermediate black holes, I mean, you mentioned that there could be other things that look kind of like it, but they're not these active galactic nuclei type of things. This would be like, I guess, star formation regions near the center of the galaxy could mask that.
Yeah, so you can get all sorts of stellar kinds of things that will mimic the same features that you would see. So for example, looking for X-ray flux is one way that people try to find active galactic nuclei because these are really extreme environments where the gas gets superheated, and so it can glow all the way up in X-rays, which is super high energy light. But the luminosities or the brightnesses that you associate with these objects, by the time you get down into the low galaxy mass regime, those brightnesses can be achieved in X-rays by stellar binary systems. So you can have compact accreting objects that are only a few times the mass of the sun that can actually give you these same X-ray fluxes, basically. So there's all sorts of stellar features that can mimic your massive black hole features that you go looking for. We also look for example, the motions, the group motions of stars. So how are stars moving around in the galaxy as groups? And so if you zoom in on the center of a nearby massive galaxy, what you see is that the stars are doing their things with their orbits, but as you get closer and closer to the center, all of a sudden they start going faster and faster, and that's because of the gravitational influence of the black hole. But when you talk about a low mass galaxy and a lower mass black hole, the distance over which you would expect those stars to be moving faster and faster in the center of the galaxy shrinks down even smaller and smaller and smaller. And we can't zoom in quite far enough at this point to be able to actually detect that kind of a signature. So there's all sorts of technical reasons why we can't conclusively say a whole lot about the occupation fraction in these low mass galaxies. And it's because a lot of other things can mimic it, or just because our technology is not quite there yet.
So what's your feeling on the impact of AGN to star formation in the galaxy as a whole? So
yeah, there's a long history here, and again, this is looking back at simulations of our universe where things didn't quite match up with what we were actually observing. And so when I'm not a simulator, I should say when people first started to try to build galaxies in computer models, what they found is that they could put in all the physics that they knew about at the time and try and sort of grow galaxies organically as a function of time in their computer simulations, and they were all too massive. They were way too big, too fast. They made way too many stars too quickly, and they did not look the way that we see galaxies when we go out and look with our telescopes. And this was a problem for a while. And it turns out that if you have a black hole in your galaxy and your black hole eats at some point and shines a whole bunch of radiation and basically deposits a bunch of energy into its host galaxy, it actually shuts down star formation, or at least slows it, and solves the problem of overly massive galaxies too fast. So it actually regulates the star formation in galaxies and keeps them from getting too big too quickly. And there's also observational evidence to help support this story that we tell ourselves. I should make it clear that this is how we interpret all of these pieces now. Doesn't mean it's the final answer or that it's completely right or anything, but it does seem that black holes play an important role in how galaxies grow as a function of time and how quickly they grow as a function of time. But they also regulate their own growth because they push away some of their food, as you might remember, and so that can slow down their growth as well. So they're sort of in a symbiotic relationship, the galaxy and the black hole. The galaxy can feed the black hole can sort of shut down the growth of the galaxy, or at least slow it. And so they regulate each other's growth. And they're very dependent on each other in a lot of ways that we still don't fully understand all the details of so far.
When I think of timescales, you think of the impact of an AGN on star formation in the host galaxy. That if that AGN is so that it's active for, let's say, several tens of millions of years, yet really you're looking at the star formation history of a galaxy. When you look at it at some given moment in time, let's say you're looking at a galaxy that's nearby and it's redder than it should be based on our general expectation, it's hard to pinpoint the AGN effect, because if you go and look for the AGN, well, it just happens to be in a quiet time now, so there's no sign of an AGN, even though it may have been extremely important to cause the if you like, the quenching or the truncation, or at least the great reduction in the star formation in the past. So the evidence of that reduced or quenching star formation is around today, but not necessarily an active AGN. You just don't see no sign of that.
Right. And that actually takes me to one of my favorite things that we occasionally find in astronomy, which is a light echo, or like sort of the evidence of a once active supermassive black hole. So there's this object called Henny's Verwoop.
Yes.
It's this name that I cannot pronounce. I think it's Dutch.
It is.
It is Dutch.
Yeah.
Yes.
And it's this green glowing blob that is outside of a galaxy, and it's just sitting there glowing. And, it's this weird lit up patch of gas in the middle of nowhere, that's just sitting there doing its thing. And, we happen to be able to see it right now because time scales worked out for us to be able to observe this. But what it is it's the light from the black hole in the center of a nearby galaxy finally got that far away from the galaxy and lit up this patch of gas that's just hanging out near the galaxy, and we happen to be able to see it right now. It's not going to do that forever. It wasn't always doing that. The timescales just worked out perfectly for us to catch it this time. And I think a few other people have found some other Verwoop-like objects, these little patches of glowing gas that are the remnant light from some previously active galactic nucleus that just happened to be lit up at this moment in time. And I think those are just super fun objects, that we can find them and that they can tell us something interesting about what was happening in the past, even though we don't see that happening anymore. So I love looking for those little markers of historical events. I think they're a lot of fun.
Yeah, I think a lot of people have done like supernovae light echoes too.
Mm-hmm.
Yes, those are cool too. Yeah.
Which, it's kind of the same principle. But so did you want to? I was just going to finish. We're at the end, I guess.
We're
right?
at the end.
But I like, before we leave, I just wanted to mention too that, our galaxy, the Milky Way, is not an active galaxy. But of course, something's going to happen to it, and roughly 5 billion years from now, we're going to merge, right, with Andromeda. So do you expect, to kind of finish this off today, do you expect that has the potential of lighting up our galaxy again to become an active sort of galaxy,
It could. It also has the potential to do something even more extreme, which is to smash two supermassive black holes together. Because if you merge two galaxies and each one has a black hole in the center, those black holes are likely to find each other and collide. And when they do that, two black holes make one bigger black hole. And we haven't been able to watch this process happening with supermassive black holes, but we have recently been able to start watching this with smaller black holes. So 10 solar mass black holes, 30, 50 solar mass black holes. And that's with the LIGO experiments, looking for gravitational waves from colliding black holes. And the first time we saw that was 2016. That was almost 100 years to the date after Einstein predicted that this could potentially be something that happens in the universe. And Einstein himself never thought we were going to be able to see this because it's incredibly difficult to detect these tiny signals. It took us 100 years, but we got there. We got there.
Yeah.
What we haven't gotten to is being able to see these signals from colliding supermassive black holes yet, but we expect that they're there just like we see the signals for the smaller black holes. So yeah, our black hole has some interesting events coming up in the future.
Yeah.
I won't say the near future because, 5 billion years is a while, but we won't be here by then. We'll have other problems with the sun coming to the end of its life around the same time. So, yeah.
That's great. Well, anyways, Misty, thank you very much for agreeing to do this today. I really enjoyed it.
Absolutely.
Yeah, it was so fun
great
to chat with you both today. Thanks for inviting me.
Thank you.
So if you're interested in science or STEM or STEAM, and it doesn't matter what it is, of course, we always hope that people will be lifelong learners for the rest of their lives. You can come join us here at the University of North Dakota. We have both online and on-campus classes that you are free to take if you like. If you're around, of course, drop in to see Robert and I. We'll have a chat with you.
Come see us.
Our next podcast will be next Tuesday on May the 14th at 3 o'clock Central Standard Time. We always leave you with a quote or an excerpt or something. Of course, Misty, I knew you were working with AGN. I did check your CV long before we did this podcast.
Long before, yeah.
And so I came prepared for AGN-like stuff. And what I decided to do, and you'll know this, Misty, but others may not know this, is to actually state a nursery rhyme parody that George Gamow published in his book back in the mid-1960s. I don't know if Robert knows this.
No, don't know this one.
Hopefully I won't kill it. I'll say it properly.
Okay.
Here we go. Twinkle, twinkle, a quasi-star, biggest puzzle from afar. How unlike the other ones, brighter than a billion suns. Twinkle, twinkle, quasi-star, how I wonder what you are. And quasars, of course, those were discovered in the 60s, so it was all new at the time, and people weren't quite sure, of course, what their nature were. But because I said that, there's also another one from George Gamow I couldn't resist saying. You ready for this one?
Okay.
There was a young fellow from Trinity who took the square root of infinity, but the number of digits gave him the fidgets. He dropped math and took up divinity.
Oh, Lord.
With that, thank you very much
Thank you
for
for being
listening.
here.
We'll see you next time.
Thank you, folks. You have a great week.